This YOLO model was trained without taking photos or scraping the internet for images. Instead, I used Blender, a free 3D software to render images using 3D models. I also built a free add-on for Blender that allows you to record YOLO labels automatically. That way you don't have to write custom code or manually label images. The end goal is to have a reusable training pipeline that can be used for quickly training YOLO to detect a custom object. Eventually, I'll try to port this over to Raspberry Pi. In this video, I'll show you the reusable scene I created in Blender and how I trained the YOLO model with it. Now, the model will be far from perfect, but it will be a good starting point. In the second part, we'll deploy a model to a Raspberry Pi to build a full end-to-end solution. In part 3, we'll talk about improving the accuracy and dive into training details. Inspiration came from this paper from NVIDIA where they trained an object detection model using rendered images. Their setup involves adding lots of distractors, lighting changes, and camera angles. I decided to use Blender to create a similar setup, mainly because Blender is widely available and popular. I also find it much easier to use. Opening up the scene, we see a large HDRI image in the background. This is meant to provide some background variation in our images. If we rotate a camera around the scene, we can see the background variation that this provides. The star of the scene is Blender's particle system. Two of these planes are configured as particle systems. One is set to emit renders of our target object, a 3D printed benchy. The other is set to emit renders of distraction objects. You can see this in the object's particle settings, where it is instancing a collection called distractors. The distractors collection contains a number of objects that we'll be using for distractions. All of these objects are set to the side here on the side of the scene, hopefully away from the view of the camera. Each of the particle systems, as well as this cube, have collisions set to on. This allows us to bounce objects off this cube so that we can get random rotations of the objects. The cube is set to not render so that it appears invisible in our final rendered images. The material of the benchy is also set to be randomized. This is accomplished with shader nodes. A color ramp is set to vary the color. A random number related to the object instance is used to pick the color on the color ramp. The result is a different color for every particle and every benchy that is rendered. Lighting variation is set using keyframes in the animation. Selecting a light and then going to the graph editor, one can see the variation in light that we've generated. Every light has some variation in this scene. To easily generate annotations, I've added the free BL Vision add-on. It's an add-on I've created myself and have provided for free on my website and on GitHub. In this add-on, we'll need to register the particle system for collecting bounding boxes. The process is to register your particles to be recorded as objects to detect. So we'll open up the BL Vision add-on, select a mode, which will be particle emitter. The next step is to select the actual emitter of your objects. In this case, it's called a target emitter. I've highlighted this particular scene or this particular frame to show some interesting aspects of this add-on. One is some blocked objects. But first, to register it, what we'll do is we will add this target emitter to our list and leave it as category 0. We'll leave that for the YOLO detection as category 0. So when we do our detections, it will be labeled as that. The next thing we'll check is raycast. So this allows us to detect whether or not objects are blocked by other objects. Right now, it has it on, and has two different options. One is fast and accurate. For now, leaving accurate in place, we'll test the bounding boxes. So in here, we found 3 bounding boxes. So 1, 2, and 3, showing that one of them that's blocked is not being counted. If we were to turn this off and then test the bounding boxes, we get 5. So it looks like there's another one that's detecting somewhere in here. So 1, 2, 3, 4. Not sure exactly where the 5th one's coming from, but not that accurate. So what we'll do then, again, going back to the accurate method, 3 bounding boxes. If you go for the fast method, it just basically shoots a single ray at an object, so it's a little bit quicker. However, if your object has holes in it, so for example, this benchy, probably will not detect it. So it only found 2 bounding boxes, so 1 and 2. It removed the one that was correctly being blocked. However, it missed this one because there's a hole inside the middle of this object where the origin is. So for this particular object, we'll be choosing the accurate method. As a note, if you were to add your own object, it will just record the name of the object and list that in your YAML file. So there's no need to do any custom changes of names. In the data output section, select your data output format. We will select YOLO for this demo. Check the box next to bounding boxes. This will tell the add-on to save bounding box labels during renders. Select a root folder where you want images and labels to be saved. Feel free to add a file name prefix if you'd like to. You can also choose custom paths if you don't want to follow the standard format. Using the standard format, this is the folder structure that will be generated. Hit Ctrl or Command F12 to render the animation. Your labels should be then collected. After your render, go to the root folder you saved to. You should see a data.yaml and folders containing images and labels. Let's take a look at one of the images. Looks like there's one benchy in this image. Let's check the corresponding label. It looks like it found one benchy. For our object detection model, we'll be choosing Ultralytics YOLO, primarily just because it's really easy to use and it'll be a good baseline to start off with. What I really like is that you can choose some simple methods in Python, or you can even use the command line to run the model and train it directly from your command prompt. But first we'll need to actually train, and we'll need to split the training data set into training and validation. They have a couple methods for this. I chose to use the auto split feature, which I've included in some custom code myself, but basically you can split it up into validation, test, and also training data sets without actually changing your directory structure. It just provides some text files that you can then reference in training, which the YOLO model will use automatically. Here's my simple code to kind of wrap around that auto split feature. It just allows me to run it from the command line where I can choose what place to point the auto splitter to, and then also allows me to change the YAML file to reference these text files at a later point. After running the code, you can see the 2 different text files generated by the auto split feature. Inside here, you can see the paths to the specific image that were picked at random. You can also see in the data.yaml file that is now referencing these text files instead of the directories themselves. Moving on to training, I'm using the standard command line from the YOLO Ultralytics website, just pointing to the folder that I am going to be training from. I'm going to freeze a few layers, 10 to be exact, and this is based off of some papers I've seen. I'm also going to put my specific device, which I'm running off a Mac, so I'm picking MPS for the Apple Silicon, and then off to training. As you can see, it starts up, takes a few seconds, but gets going, and now we just wait. So I stopped training early just for demonstration purposes, but we're going to take a look at some of the results that were generated. So we'll look at train batch 1, just to take a look at it, see what we were able to see. So it looks like the model is able to detect a lot of the benchies. Pretty good. Then we're going to actually able to get these labels from a very little work. So I'm going to go into something that I actually trained earlier. I'm going to go into the best one I have so far. We'll look at the validation batches, because those things are basically what you're going to tell you what the model is going to predict in real life, at least closely. So see here that we've got some pretty good results. I mean, looks like it's detecting benchies for the most part, not really anything else. So we're doing pretty well. So in the next video, I'll be going over how to port this over to the Raspberry Pi, hopefully the AI camera if I can. Just quick looking at some of the other results that are here. I'm not going to go into detail about these specific training metrics, but say for example, a confusion matrix, it doesn't really look amazing, but it's a good starting point, I think. So stay tuned for the next video. Hopefully I can have it out in the next couple weeks.